A new survey has just mapped the large-scale structure of the universe in unprecedented detail. It was designed to answer a very specific question: how matter is distributed across the larger scales we can observe. At those scales, cosmology expects structure to fade. Galaxies and clusters should blur into something smooth and uniform. But this survey does something new. It gives us enough information to look at that expectation from two different angles. And depending on which one you take, the universe you recover looks very different. The idea that the universe becomes smooth on the larger scales is not a prediction of the Big Bang, it's required to make the equation solvable. Modern cosmology is built on a particular kind of geometry, one that assumes that space can be treated the same everywhere, once you zoom out far enough. That assumption is what allows cosmologists to talk about an average density of the universe, a global expansion rate, and a cosmic background that everything else sits on. Without that smoothness, those quantities cease to function as single global parameters. In a prediction, you start with a model and then check whether the universe behaves the way the model says it should. But with homogeneity, the logic runs the other way around. You have to assume the universe is smooth first before you can write down the equations that describe its evolution. Only after making that assumption can you talk about expansion, curvature, or the age of the universe. If homogeneity is something the equations require, then it becomes an empirical question. At what scale does the universe actually behave that way? How far do you have to zoom out before structure stops mattering, and a meaningful average really exists? That's not something theory can settle on its own. It can only be answered by observation. And that's exactly what large-scale galaxy surveys are designed to do. They don't attempt to map the universe object by object, but to summarize its behavior across enormous volumes. To do that, they rely on averages, correlations, and scaling relations. These are ways of compressing complex structure into a small number of global descriptors. But those tools only work if the universe can already be treated as smooth on large enough scales. The analysis then focuses on how real galaxies deviate from it. Densities are written as fluctuations around a background value. Correlations are measured relative to that background. Structure is treated as something that sits on top of an already defined average universe. The average density is never established independently. It's built into the statistical tools used to analyze the data. Those tools are designed to measure departures from homogeneity, not to test whether homogeneity itself has actually been reached. The Dark Energy Spectroscopic Instrument, or DESI, is one of the most ambitious galaxy surveys ever undertaken. Installed in the Mile telescope in Arizona, it was designed to measure the position and distances of tens of millions of galaxies and quasars across a large fraction of the observable universe. By capturing thousands of spectra at once, DESI maps the large-scale distribution of matter in 3 dimensions, allowing cosmologists to study how structure is arranged across vast cosmic scales with unprecedented statistical precision. DESI contains enough information to ask 2 different questions. Can we recover the average density in the data by looking at the deviations from the average? This is the question that cosmologists consider settled, because, within the framework, the DESI results function as reinforcement. The more fundamental question is, does an average density exist at all? This is not a question that most cosmologists ask because the framework treats the question as unnecessary. But if a true average density exists, then we should expect something very specific to happen as we change scale. On small scales, density varies wildly. Galaxies cluster, voids appear, but as you increase the scale you're averaging over, those variations should begin to cancel out. And eventually, it should converge towards the same value everywhere. That convergence isn't a detail. It's what makes the idea of a global average meaningful in the first place. If the density never settles, if it keeps changing no matter how large the scale, then the concept of a single cosmic average stops being operational. You can still define one mathematically, but it no longer corresponds to something the universe actually exhibits. This is where the work of Francesco Labini becomes important. In simple terms, he asks that we shouldn't assume an average exists before checking whether the data actually converges towards one. Instead of starting with a background density, Labini's approach asks a simpler question. If you measure the density around galaxies themselves, and you increase the scale of that measurement, does the density ever stop changing? If an average density truly exists, this method should reveal it. The values measured in different regions should begin to agree. The system should self-average. In standard cosmology, structure may evolve with time, but homogeneity is still assumed to hold at each epoch. Changing the depth of a survey may change the amplitude of structure, but it shouldn't eliminate the scale at which densities converge. If that convergence never appears, then the assumption fails regardless of how structure evolves. What DESI allows us to do for the first time is apply this test over an enormous range of scales using carefully controlled samples. And when the test is applied, the convergence never clearly appears. The density keeps changing, the clustering persists. The average the model assumes never fully reveals itself in the data. At this point, it's tempting to stay with the data, but the more important question is simpler. What does it mean if convergence never clearly appears at all? If the universe doesn't settle into a well-defined average density, then several things we normally take for granted stop being automatic. The idea of a single cosmic background becomes harder to justify. Quantities like the expansion rate and the mean density become increasingly dependent on how, and more importantly where you measure them. DESI is not a marginal survey, it's the most precise and expansive map of large-scale structures we've ever built. And the result isn't subtle. The convergence that modern cosmology requires simply does not clearly appear. What's being revealed isn't a failure of observation, it's something deeper. Modern cosmology contains a set of assumptions that quietly reinforce one another. Homogeneity is assumed so that an average density can be defined. That average is then used to describe structure as a fluctuation. Those fluctuations are analysed with tools that already presume the background exists. And because the background is built into the model, the analysis inevitably recovers something that looks like an average even when the data itself never truly settled into one. For a long time, this loop was hard to see. Surveys were small, noise was large, the scale where convergence was expected always lay just beyond reach. But as our instruments have improved and surveys like DESI have pushed to vastly larger scales, that self-referencing structure is starting to unravel. Not because the universe has changed, but because we can no longer rely on assumptions that were never independently tested. What we're seeing isn't chaos, it's structure that persists longer, farther, and more coherent than the framework we're using was designed to accommodate. And when a model begins to explain reality by quietly assuming the very thing it needs to prove, increased precision can have very different effects. Precision applied within the assumed framework strengthens it. It sharpens the measurements, tightens the fit, and reinforces the assumptions the framework already depends on. But if we step outside that foundational assumption, precision does something else entirely. It starts to expose the flaws. DESI is showing us that the same underlying question gives different answers depending on how it's framed. The same data is revealing two very different versions of reality. What's striking is that nothing about the physics has changed, the observations are the same, the maths is the same, the difference lies entirely in what is treated as a conclusion and what is treated as a premise. For the first time, the scale and quality of the data are sufficient for this distinction to matter. Not as a philosophical objection, not as an alternative theory, but as something revealed directly by the data itself. The same measurements now support two internally consistent descriptions of the universe, depending on whether homogeneity is assumed or tested. And that leaves us in an uncomfortable place, because it suggests that modern cosmology is doing more than simply refining its picture of the universe. It may quietly be reinforcing a particular version of reality by how the questions are framed. The data hasn't changed, but the moment we stop assuming the answer in advance, it begins to tell a very different story.